Hi, I'm Bo. In this work, we study optimizing multi-touch textile and tactile skin sensing through circuit parameter estimation. The textile and tactile sensor has emerged as a novel technology for human-robot interactions. The sensor itself is purely made of textiles, and it can be scaled to a large area or customized to adapt to complex surface geometries. Textile and tactile sensors also have a very low material and fabrication cost. Due to these properties, it is called robot sweater. The textile and tactile sensor follows the sensing principles of resistance sensors. The top and bottom layer is made of alternating conductive and non-conductive stripes, which forms a grid of sensing cells. When force is applied to a cell, the resistance between the top and bottom layer drops. We can then detect the change using the analog to digital converter. However, signal processing of textiles-based tactile skin still poses a great challenge due to it being noisy and subject to ghosting effect, where false detections occur due to alternate electrical paths. This degrades the accuracy of multi-touch force sensing. To tackle this challenge, we proposed the very first optimization-based method applied to a resistive sensor array model to solve the problem. We formulated textile sensing as a resistive parameter estimation problem. We solve for the resistive parameters across the skin and predict the contact forces given the voltage measurements across the rows and columns. Our proposed signal processing framework comprises two stages: offline single-touch calibration and online multi-touch force estimation. In the calibration stage, the robot presses on each of the cells, relating the skin resistances to force. In the force estimation stage, the optimization program solves for the skin resistances, and with the calibration model obtained offline, we can predict contact forces. So how do we solve for the resistances of the skin? First, voltage measurements are made for each cell by applying different voltages across the rows and columns. Second, a naive resistance estimation of the sensing cells is made by directly applying Ohm's law. The circuit simulator simulates the voltage at each node of the circuit, and the result is used to initialize the solver. Third, the optimization program solves for both the cell and wire resistances. Let's dive into the optimization program. Here we show how the optimization program estimates the wire and cell resistances. We first constrain the circuit parameters to satisfy Kirchhoff's current law and Ohm's law. Then, we minimize the discrepancy between the estimated voltages and resistances across measurements in the time window. That is because we expect the physical properties of skin only vary slowly over time. Finally, we apply regularization to the solution by penalizing low wire resistances. The intuition of this penalty comes from the assumption that the contact on the skin is more likely to be sparse across a large area. We conducted two experiments in simulation that varies wire resistances and cell resistances. Compared to the ground truth, the naive approach, which ignores wire resistances, shows widespread ghosting effect. The feasible solutions eliminate most of the ghosting phenomenon, and the optimal solution achieves even better results through regularization. The results shows that our algorithm effectively reduces the sensing error across a wide range of wire and cell resistances. We tested our framework on real textile skin on a flat surface. The non-contact blue cell and then the red cell is supposed to display significant ghosting effect, but it is largely mitigated by our algorithm. The reduction in force estimation error is verified by comparing our results to the ground truth force torque sensor readings. Our algorithm is also robust against the change of surface geometries. As seen in the video, the skin is attached to a cylinder object. The ghosting effect is also largely mitigated on the curved surface. The reduction in force estimation error is also seen when compared to the ground truth force torque sensor readings. Due to our capability of estimating wire resistances of the skin, we can simplify the textile and tactile skin structure to only two layers without the middle layer that is used to apply a force threshold physically. The removal of the middle insulating layer allows the skin to detect forces as slight as 1 Newton. As seen in the video, multiple 100-gram objects are placed simultaneously on the skin. Our algorithm accurately determines their weights while eliminating ghosting effects. Our optimization method mitigates the ghosting effect while enhancing multi-touch force sensitivity and lowering activation force. This allows us to further simplify the structure of the textile and tactile skin.